All right, well, welcome back. I hope everybody had a wonderful lunch. Get stretched out here. Everybody's stomach is full. Give you about 5 minutes. You should be all asleep. And then I'm just going to stop, and then when you hear the bell, that means it's over with. So, again, it's quite an honor to come out and share the research that we're doing in the U.S. on firefighter safety. And although I gave you a little snippet of the positive pressure ventilation work that we were doing in the earlier presentation, hopefully this will clear up any of the questions that you have as I can spend a little more time on it. It was a joke that we create really large reports, but the truth is there's a lot of information in there. And if I wanted to do a full course on one of our projects, it can be anywhere from an 8-hour to a 24-hour class, depending on how in-depth we want to go. And I don't think any of you want to sit here for the next 24 hours, so we'll do the abbreviated hour-and-a-half version. I'm quite okay with questions in the middle, especially with a lot of this research stuff. It's much easier to answer a question when there's a visual up there, so if you have something, let me know. We'll try and explain it a little more. I've also buffered a little time in the presentation to be able to answer questions throughout, so in case we go right to the end. So as I said before, we're going to talk about positive pressure attack. This is use of fans to control flows within the structure before any water is placed on the fire. And to initiate that, we have a short video on the project just to kind of give you the background.
Here at UL, we have one of the most unique lab facilities worldwide. We're able to conduct everything from small rooms on fire to multiple houses on fire to warehouses on fire.
We're here at the UL Large Fire Lab in Northbrook, Illinois, a 100-foot by 100-foot structure with a 60-foot tall movable ceiling. It's one of the largest land-based elevators in North America.
This is probably the closest thing to the actual fire ground you'll see. It is a controlled environment, but the fuels that we're using are the exact same fuels that we'll see out in the real world.
The houses are different based on the layouts. The two-story colonial has an open floor plan, where the single story has a confinement or enclosed floor plan. Firefighters only have one opportunity to see each fire. They're not able to test variables within the fire to determine the best tactics to utilize. We're capable of testing 24 different experiments to look at the variables that they can't look at in an individual fire.
UL FSRI attacks a problem that is actually existing in the fire service. This research helps us to get behind the scenes and get to the why of what we're doing things as opposed to just the what.
We get to measure everything that's going on within that building. And so you're learning the why.
This project in particular is using high-powered fans or positive pressure fans to affect the flow path within a structure.
Object is to create a flow through the structure so the firefighters can make the flow go where they want it to go. Previously, we've examined horizontal, vertical. This gives us the third component, the positive pressure, where this will be the only set of experiments in similar structures that have ever tied the three of those together. So not only are we looking at positive pressure, we actually have a baseline now where we can actually compare it to horizontal and vertical as well. So does that mean, well, we're going to pick which is the best of all of them? No. We're going to give you some knowledge so you can make those tactical decisions when they need to be made. We're going to ignite the fire in the great room in the back of the structure, allow it to grow, and then we're going to simulate the fire department arriving.
The air inlet will be the front door. The first exhaust will be the family room window. Then we were going to open a window on the second floor to see if having an opening remote to the initial opening is going to affect how the air flows within the structure when there's a fire.
And as we create that low pressure, fire dynamics tells us that that heat is going to move towards that window. Well, we've got a number of measurement sensors here to be able to show us what's going on. So we've got temperatures, floor to ceiling. We've got a gas concentration measurement down here. So if we were to have an occupant that was trying to get out of their bedroom and they collapsed at the top of the stairs up here, we'll be able to tell how survivable is this location, and did the fire service make it better or make it worse by using their tactics.
The variables within our experiments are the inlet size, the exhaust opening, the fan positioning, and the hose line used for suppression.
So going through the doorway here, we have bidirectional probes and thermocouples. Put the pressure measurement with the temperature measurement. We're able to tell how the gases are either moving out of the structure or moving into the structure.
We are able to use data, sensors, and video to reproduce fires and allow them to determine when and when not to use positive pressure ventilation in residential structures.
We talk a lot about positive pressure and negative pressure inside the structure, outside, where the air track is. But being here, we are able to see what's going on with the fire behavior and real-time pressure changes based on the monitoring equipment inside, and then what happens when those pressures drop and how quickly they drop inside.
Pressure is equalizing out. Our ceiling temperature is still around 600 degrees, about 350 at the floor.
Some of the stuff that we've learned in the previous studies, and tactically it made sense because it matched up with different things I've seen on the fire ground.
It is more than just science-based. It's a collaborative effort and a relationship with UL and the firefighters to bring it to real-world application.
We can make science-based decisions that are going to impact firefighter safety and civilian safety and reduce fire loss.
Ultimately, we want those firefighters to have the information to make them most efficient and safest, so that we're improving their knowledge, building on their experience, and ultimately improving the safety of the street-level firefighter.
So that's the easiest way to kind of give you a general overview of what we're looking at, but also kind of put you in the position of being in our lab when we're doing these experiments. We were fortunate enough to be able to fly a drone inside the lab to give you kind of that aerial picture of there. Produce some really nice video footage, but it also kind of gives you a perspective of how large the space is. One of the biggest questions we get when we're doing this type of research is, you're doing it inside a building, so it obviously cannot be the same as if I was to do it outside. And the answer is that's absolutely correct. We're not taking into consideration temperature change. We're not taking into consideration winds. We're not taking into consideration rain. But the reality is if I had to do that, I would have to wait until the temperature is the same, the wind is the same, and the conditions are exactly the same before I did each experiment, and it would take us a lot longer to be able to identify the same things that we can identify in the lab. The space is also so large as compared to the structure. It's on an order of about 20 times larger than the interior volume of the structure, that it really has no effect on the physics. It's also exhausting all of the products of combustion out, so they're not building up in the building and causing additional trouble. So it is inside a building, it is inside a lab, but that lab actually gives us the ability to look at different variables and not have to take into account the wind being different. Because if the wind happened to be different, I cannot compare experiment A to experiment B. So that becomes a challenge. We do experiments in the field as well. It's just for these larger projects, it's much, much easier for us to kind of do them in the lab. So how do we bring the vast fire service in the U.S. together to work on one of these projects? It's a challenge. There are estimated to be about 1.1 million firefighters in the U.S. That's an estimation because there are so many that they cannot accurately capture which ones are actually firefighters, which ones are members of a fire organization but still not actively fighting fire, and which ones are retired life members of those organizations and just on the rolls. So 1.1 million is the number we go with. About 300,000 of them are career firefighters, and that's a very accurate number. We know that one because they get paychecks. If the paychecks stop coming, we know they weren't a firefighter anymore. But it's a challenge to bring that many people together to work on one project. That's never going to happen. So we take and put out an application for a technical panel. And these are individuals who we put it out on our social media channel. We will invite specific individuals to apply to the panel that we believe really could produce the most benefit to it. And then we'll look at all the applications, and we have to whittle it down to somewhere. Our goal is to get it down to 20. We have yet to get it down to 20. There is always more than 20 qualified applicants that we need to have on the panel to be able to have the best cross-section of the American Fire Service. In this particular project, we got it down to 26, and we included 2 additional members from outside the U.S. Those are not funded by the projects itself. The projects are all funded through the Department of Homeland Security. UL thought it was very important that we, as we talked earlier here, collaborate with other countries because they have the same challenge as we do. And in some instances, they're using this type of tactic more than some U.S. fire departments are. So it became important to include them, including 2 additional members from Canada. So it ended up being 22 firefighters from the U.S., ranging from a firefighter who I believe has 2 years experience all the way up to some with 35 years experience, and all different respects of experience level based on where they respond. 500 years of combined fire service experience. So I assume getting firefighters together here is much like getting firefighters together in the U.S., where you put 26 different people in the room and you have 26 different opinions, and all of them want to talk about their opinion. So for a full day, we try and develop the actual project. We take project objectives that we used when we applied for the grant. So the method of this is there's a grant period every year in the U.S. for us to apply for research. There's a very small amount of money comparatively to the money given to the U.S. Fire Service that goes to research. We apply for that grant. If we receive the grant, then we can put a technical panel together to develop the research. So we have to come up with project objectives. Our primary project objective is always to increase the knowledge of the fire service. If we can get knowledge out there, we can have more effective tactics. Effectiveness is very relative. What makes one more effective than the other? When your goal is to put a fire out and all of the fire goes out, does that mean they're all absolutely as effective as they can? And the answer is, of course not. Sometimes we do a great job, and sometimes we'd like a second shot at it because it didn't go as well as we'd hoped. This way, we can hopefully narrow down the knowledge so that it allows firefighters to do their jobs safer and more effective at the same time. If you were in here earlier, I talked about the difference between positive pressure ventilation and positive pressure attack. It's a very significant difference in the U.S. There are departments that will never use a fan before water is on the fire, and then there are departments who will start the fan before they even charge the hose line. So very vast difference. We defined it in the project as if you're doing positive pressure attack, that means you intend to influence the fire, so you haven't put water on it yet. If you are doing positive pressure ventilation, it means you intend to remove all of the products of combustion from that structure using the fan. So if there's an uncontrolled fire, you're doing positive pressure attack. There are some instances where you think you're doing positive pressure ventilation, and you may actually be doing positive pressure attack. You find out very quickly. This is the slide I had up earlier of the goals. When we started to get our technical panel together and develop these research experiments, we need to really determine why we're doing what we're doing in the fire service. That way we can get the best knowledge from it. So going back to the books, trying to figure out why exactly we're doing this, and the most prevalent reasons out there were to make it better for firefighters inside, make it better for victims inside, and reduce damage. Those were the reasons that they have it. In the U.S., they call it venting for fire, which is allow the fire to grow slower, or venting for life, which would be a firefighter or a potential victim. When we look at that, we need to know, how do we effectively accomplish that with ventilation? Because if our ventilation doesn't make it better for victims inside, and it doesn't reduce the temperatures inside the structure, and it doesn't make it easier for firefighters to put out the fire, I would consider that ineffective ventilation. But how do you know if your ventilation is effective when you can only look at one fire at a time? You have to understand the physics and the chemistry and the fire dynamics that go behind that to be able to come up and make good, educated decisions. Here's a little bit more in depth in our two structures. If somebody's back there, could we play the video in the upper right there? the single-story test fixture and the two-story fixture. This one is roughly 1,200 square feet, 3 bedrooms, 1 bathroom. This one is 3,200 square feet with 4 bedrooms, 2 bathrooms, and 12 total rooms. This is what it looks like if you time-lapse the construction of these. They build them in approximately, the structure itself goes up in 3 days. The interior drywall finishing takes about another 4 days, and they can build those structures in our lab. They do not have any heating, ventilation, or air conditioning systems in there. There are no electrical systems in there. The whole reason behind that is we're looking at content fires and not structure fires. If we put those systems in, there's always the potential that we would have a structure fire, and our lab is great for burning things, but we cannot burn that entire house at the same time and still have a lab left. So we have to make some trade-offs and try and understand those things. In this particular set of experiments, we actually made some holes to simulate where electrical outlets would be or where lighting fixtures would be to see how the use of this ventilation tactic affected whether or not you could move fire from the room into that space. And we'll talk a little bit about that. This is what our instrumentation layout looks like. The green dots you see on there are temperature. We do temperature at 4 different heights. They're 1, 3, 5, and 7 feet, but those correspond with things that we're interested in the structure. So at 7 feet, I'm interested in the upper gas layer temperature. That's a foot off our ceiling. Most likely that's going to give us the most representative upper gas layer temperature we can get. At 5 feet, you're the average walking height of someone walking through that structure. So I'm looking at the temperature roughly of where someone's face or respiratory tract would be while they're walking through the structure. At 3 feet, I'm representative of a firefighter crawling or ducking low through that structure. The intent there, how are the conditions for them if they're trying to get under smoke? And at 1 foot would be a victim lying on the floor in that structure. So we monitor that temperature at that point. That's why we do all 4. We also occasionally will throw more in there to try and determine the effects of that upper layer movement on the fire. And the best way to do that is with some temperature. So green dots are temperature. We have temperature in every room. Blue circles there are gas concentrations. We can measure CO, CO2, and oxygen. As we saw earlier in the presentation about exterior fire attack, oxygen just doesn't really seem to be a significant concern in these fires for occupants. And my thought on that is mainly because of how fire burns. If fire needs oxygen to burn, and all the oxygen's gone from the structure to the point where the fire can't burn anymore, does that mean people can still survive? And the answer is yes. If there's any fire safety engineers in the audience, you've heard of oxygen reduction systems that are designed to protect like computer storage rooms or cold storage warehouses, where they take nitrogen and they pump it into the room to lower the percentage of oxygen down to roughly somewhere between 14 and 16%, which reduces the chance of ignition from fire, but it also reduces the ability of the fire to burn efficiently. Well, when we hit 14 and 15% oxygen concentrations in our structure, that's when the fire starts to decrease in size. So we never get down to that 6% oxygen concentration that they were using as their threshold. We happen to use a little bit different formula, but it's the same concept. We never get to that point. So oxygen doesn't really become a big concern because the fire goes out before you can get to 6% oxygen if it's just burning naturally in there without any intervention. Whereas CO is a very important factor, and CO2 is also an important factor. There are engineering calculations that allow you to use the amount of CO and CO2 within a structure to calculate what's called the fractional effective dose. CO2 makes you breathe faster. So if you're breathing faster and there's a lot of carbon monoxide in the atmosphere, you're going to receive that carbon monoxide into your system faster. I'm currently working with a couple of physicians in the U.S. to try and determine at what point your blood carbon monoxide level actually becomes a fatal level. So you could use a threshold criteria of a certain concentration of carbon monoxide in the structure, and that will work effective for what you're intended to do. But if your goal is to know when someone is can potentially survive that, regardless if they're conscious or unconscious, you need to know at what level their blood oxygen can get to. because just because they're in the atmosphere, it doesn't mean they're receiving CO. If they've gone unconscious and are no longer breathing, we know that we can revive people from that state, so they are no longer receiving CO into their system. It turns out the point at which most fire victims in the U.S. have a carbon monoxide blood concentration is about 60%. If they're above 60%, it's a fatal. If it's not, they can usually bring them back from that. So we use that threshold of a 60% COHB level, it's called. We do pressure in the structure. Those are the orange points in there. They're located in most of the rooms. We thought we could use pressure to determine how air flows. We are partially correct on that instance. If I solely use pressure to determine how air flows, I would not capture the fact that part of the door is flowing in and part of the door is flowing out. I would just capture that the living room has a higher pressure than the outside, so I would assume it's all flowing out. When in reality, I was pushing a whole bunch of air into that structure, so that's what I need to configure that. Hans?
You're mentioning differential pressure, but you only get one pressure point. Is that you're doing the differential measuring with
between the inside and the outside of the structure is our differential pressure measurement. And those are actually at 3 different heights. We measure the pressure 1 foot off the floor, in the middle of the structure, and 1 foot off the ceiling. That the upper layer gas temperature, or the upper layer gases, have a higher pressure than the actual lower point. That's why we see buoyant flows in structures. And one of the reasons we see buoyant flows. So we measure at 3 different heights to try and put that all together. Coincidentally, with the fans, the way they're pressurizing the structure, all 3 of them are within like half a Pascal of each other. So in reality, they're within the error of my measurement, so I can't really determine a difference there. And then we use bidirectional probes for gas velocity. We put those at all the openings we plan on making. We also put them at the openings of the doorways. Bidirectional probes are used to measure, well, they originally were developed to measure the speed at which fire gases were moving or rising in a buoyant plume. We've taken the concept to be able to measure how they're moving horizontally throughout the structure. We can have a room that's completely involved in fire or flashover, and these probes will survive, so we can leave them in there to get velocities. Gases, the velocity itself is very dependent on pressure or on temperature, so at each one of those points there's also temperature. This is what the 2-story looks like. Very much the same instrumentation, with the exception of, instead of in the single story where everything's very compartmentalized, in the 2-story it's not compartmentalized. Every room in this building is open to this great room by a doorway. That creates a significant challenge we'll talk about in a little bit about positive pressure. Here's a second floor view. You can look down into the living room or the foyer from there. There's a hallway that runs across. We have multiple temperature sensors, pressure sensors, and gas concentrations also within the structure. The concept here is when a firefighter goes to a fire, they get experience, but that experience is from their viewpoint, wherever they happen to be. So if they happen to be in this bedroom and things got better, how do they know what made them better? Was it them closing the door? Or was it someone opening a door on the other side of the structure? Was it someone applying water to the structure? They can't see that all throughout, but we can actually capture that on instrumentation and essentially be everywhere at once. So we did 15 single-story experiments and 10 2-story experiments. Talked a little earlier about how many graphs and data that put together. My number was wrong there earlier. As I went back through, I found a whole bunch of channels of data I didn't graph, so it went from 750 to in excess of 825 graphs, which added more time to go back and go through those. We had the 500 visitors, opening it up to anyone who wanted to attend that could pay their own way to come to the experiments. They were welcome to register and show up. We had roughly 50 firefighters a day. It's a pretty interesting experience for them. Not only did they get to meet with us in the morning and we would walk them through the structure and tell them what we were going to do for the day, then they watched the first burn. We had lunch with them and described what we saw from our end and talked about what they saw from their end. We did a second burn, and then we did that one more time, talked to them, and then we went back to the lab to set up for the next day, and they got to go home. So we did cold flow experiments. I talked about that a little bit earlier, and just wanted to show the again the constant or average value of all the fans that we were using when I compared electric fans to gas fans, and this time instead of comparing how much air flows out of the structure, I'm comparing how much air can physically get into the inside of the structure. So that's taking into account the air that's coming out the top. And I was able to essentially say that a gas-powered fan, which has a much higher velocity and a much higher CFM rating, or liter per minute rating for, or cubic meter rating when they're sold, produced about the same flow within our structure. So it was really dependent on the structure and not as much on the fan itself, which allowed us to pick the average fan to be used in the experiments. So one of the things that struck me right away as we finished up these cold flow experiments was, so if the size of the fan doesn't matter, why do we increasingly provide a more efficient and larger fan? What are they intended to be used for? So I started asking some firefighters, why do you need the bigger fan? Well, it moves more air. Okay, and it produces more pressure. I agree with that. What does that increased air and increased pressure do for you? And that's where we started to run into a concept of, well, that depends on where you're using that increased air and increased pressure. If I want to use it in a 10-story building to push air into the stairway so that the stairway is clean for evacuations, I need a lot more pressure because I have to overcome the weight of the air itself. If I'm using it in a single-family dwelling, it may not be as important how much pressure I'm created. It might be more important how much flow I can create. So bigger is not always better. And as I said, we saw so much flow come back out of the structure, it would indicate that we're putting too much air in there. Our intent should be able to put enough to redirect the flows, but not necessarily add more oxygen to the fire. The more we add, the bigger problem we have. The more we're entraining and moving air in that structure, the more we're increasing the fire size. Flows are very exhaust dependent, which makes absolute sense. If I have a balloon and it's got one pinhole in it, the air will come out at a slow rate. If I put 5 pinholes in it, it'll come out 5 times as fast. The structures work very much the same. The more holes you make, the more air you can move. The problem becomes, where should you make those holes? You want to make those holes so that the flows are going in the directions that you intend them to, and not creating flows that you don't expect. So this is the one we talked through earlier where we were looking at a fire in the bedroom, and we are intending to make the flow go through the living room and go out a back bedroom window. When we tried to do that with just one bedroom window open, we didn't see enough pressure differential in there to allow all that flow to go in through the door. The whole volume acted almost as one pressure zone, and all of the air went in and it moved around. Some came out the window and some came out the other opening, which happened to be the door. When we opened up 2 windows, the pressure in that bedroom was approximately ambient. At least my differential pressure sensor couldn't read any difference between the outside and the pressure in that room, which means there was a much greater difference between the pressure here and the pressure there, and it was flowing through that door. In reality, as a firefighter, that's all that matters to me. I don't really care if it's flowing out the window or burning inside that room, as long as it's not coming back out of that room, because that was my goal. If this room is where I'm using that ventilator fan, that room is not survivable. That room is not survivable for a firefighter. So it doesn't really matter in that instance because I know I'm creating that unsurvivable space in here. The idea is to use it to protect the rest of the space. This is where I was talking about the setback earlier, and just to clarify, it is taught that you can move that fan forward and backward, and that will determine the different flows within the structure. What in reality is happening is it is changing the pressure. It's not changing the flow because it's still seeking the lowest pressure and coming out. We saw a difference when the fan, and we tilted it at 2 different angles to look at that as well. This one is tilted at 15 degrees, and this one is tilted at 20 degrees up at the opening, assuming that when we tilt it further up, we'll see more flow because we're covering so much more of that opening. In reality, we just didn't see that. I mean, it's a difference between 3,000 and 3,500, maybe about 3,700. But you have to remember how I'm taking that measurement. You can't measure flow of hot gases through an opening very easily. You have to use bidirectional probes. They're not particularly accurate, plus or minus somewhere about 10%. And that could mean I'm really flowing 3,000, 2,700, or 3,300, depending on what's actually going on. So there's a little variation in there, but relatively steady. If that line if this were to go up here and peak and come back down, we'd know that that position setback was the optimum setback to the fan, and we just really aren't seeing it. We're seeing a little bit of it, but when you're talking about moving that fan back at 2-foot increments at a time, and the difference between being at 7 feet and being at 11 feet is like 2,000 CFM, if I can even accurately measure it at that, it doesn't really seem to make a difference. But it does make a difference on pressure. So here I'm looking at the difference of when I'm at 3 feet back, I can create 7 pascals of pressure in the structure. And when I'm at 7 feet back, I can create my maximum pressure, or about 11 pascals of pressure. When I tilt the fan back a little bit more, I can create somewhere between 9 pascals and 12 pascals. I am sealing more of that opening. I am creating more of a high pressure in there, but it doesn't always result in more flow through the openings. Same was true for our 2-story structure, which means we might actually be onto something. However, it is a little bit more of a peak. Now we're looking at the difference between 4,000 and 6,000 CFM, and now all of a sudden I'm out of that error range of my sensor. My theory in this one is because you're going upstairs and out a second floor window, you need more pressure. So if moving that fan forward and backwards creates more pressure, in that particular instance, it will most likely create more flow. And here's the difference in the pressure we're looking at there, where we can still do about 11 pascals, but when we have that higher pressure, we can push more out the upper opening. So I talked a little bit about the unidirectional flow through the door and how that's really not achievable with the fan. It's all acting as one pressure zone. It's seeking that low pressure, and it just happens to be at the top of the door based on where you were blowing the air in at the fan. If you were capable of elevating that fan up at 5 feet and pointing it directly at the top of the door, most likely you would see flow start to come out of the bottom of the door rather than the top of the door. And it's all because there's not a uniform flow on that doorway. So if you have a compartment fire, you have 2 zones in theory. You have a upper layer and a lower layer. In the lower layer, you have close to ambient temperature air that is being drawn into the room itself, creating some reaction with the fire, which creates heat, light, and all the products of combustion. And that creates a hot upper layer, which is coming out of that room. If I were to take a fan, which does not blow uniform air, it's not like wind coming at the side of a structure. It is using a impeller to create this velocity. It's not going to have a uniform flow. So if I take a non-uniform flow and point it against another non-uniform flow, the chances of getting one uniform flow are very, very slim, and that makes sense. So if you're looking at the front of the structure, most of the literature out there prior to this research said, I need to look at what's going on right here at the top of this doorway to tell me whether or not my flow is effective. So we start the fan up, and that's me. That's proof that I'm a firefighter. For the other ones that were proof that there's a firefighter, that's proof that I'm a firefighter. And you notice in this opening, although I've changed the flow that was there, I've decreased it a little bit, you still have flow coming out the top of that opening. And one of the big indicators in the effectiveness of an exhaust point is the neutral plane. Where is that in there? Where is it flowing out versus it flowing in? In our instance, our neutral plane didn't really change very much from when we had the fan off to when we turned the fan on. Our flow changed, but our neutral plane didn't really change. So it's really not having a significant impact in there. The answer to that is there's a lot of fire service members who think that they need to have somebody watching that fan at all times, and that person standing at that fan is going to be able to turn the fan off when they see something adverse happen. When in reality, you really can't see something adverse happen if you happen to be ventilating out the back of the structure. So it can't necessarily tell you exactly what's going on the inside of that structure. When you compare that to the exhaust flow, so in this instance we have no fan running, and we have fire coming out the top, we have a gravity flow coming down in the bottom of the window, and we have a neutral plane about here. After a little bit, we'll turn the fan on, and you'll actually be able to see the difference between the flow without the fan and the flow with the fan. It takes the neutral plane, it drops it down to the windowsill, and that is all flow coming out of that structure now. So what that's doing now is telling me that I have an unimpeded path from where I put the fan in the front to where it's coming out the window. If for some reason I started a fan and I was looking at that and the neutral plane stayed in the middle of the window, I would know it's blocked or I don't have enough flow, one of the two. So I could go back and make a change to affect that to make it more effective on the inside of the structure. But I can't see that from the fan, so you actually need to have a constant look at both of them to be able to identify, is there a sufficient flow? This will not identify if there's too much flow provided, though, because you can only push out so much, so it's not going to tell you that you're building extra pressure up inside there. One of the other interesting things that I didn't think about when we started these experiments, but became quite apparent as we got through it, was the effect that this amount of, or the size of the fire or flames out that window, what they indicated. So if we have a room that goes to flashover and becomes ventilation limited, some believe that that room is wall to ceiling, floor to ceiling, wall to wall flames. If you were able to walk through that, which you cannot, you would see flames in that entire space. In reality, that room does not have enough oxygen to have flames throughout. The flames are only at where the oxygen is available, and where that flame or where that fuel hits the oxygen at the appropriate temperature, you have combustion, which is the flame, which then produces energy, which goes back into the room. With our fans, we're blowing so much of that fuel so far out that window before it ignites, we're actually able to make all the burning happen outside the room instead of inside the room. We still have some thermal feedback going on. It's still heating up the inside of that room, but it's nothing like we were before. And what really struck this to us was when we looked at putting a fire in the living room, where our fan is blowing into the front door and the exhaust point is the living room window. And what we saw was the temperatures in the rest of the house went down. And to me, that was like, I don't understand. I'm putting a fan into the fire compartment and I'm making the fire bigger. The temperature in the rest of the house should go up and not down. And when we got back to reviewing video, we started to look at some more of our temperature sensors. It became obvious that the pressure that was created was pushing the flames out the window, and there was no burning going on inside the house. It was all going on outside the house. So even though my fan was making that really nice, great fire come out the front window, it was making temperatures lower in the rest of the house. So we talked about that unidirectional flow not being able to be achieved at the front door, but does that mean that our positive pressure attack is ineffective? And in reality, it doesn't mean that our positive pressure attack is ineffective. We have to keep in mind our intended use of the fan. We're going to control the products of combustion to reduce temperatures and make it easier for firefighters to get in there and suppress the fire. So in this instance, if I have a fire in bedroom 3 and I have a window open in bedroom 3, and I start my fan and I try and blow air through bedroom 3, I'm going to get to a point where I'm still having flow come out that front door. This is the measurement of that flow at that front door right here. So I'm still having flow come out the front door. But while I'm having flow come out the front door, the only room that I'm seeing elevated temperatures in is that bedroom, the pink line, which is bedroom 3. These temperatures are at the 3-foot mark, or the crawling firefighter mark. The rest of the rooms are all below 93 C. That's well below the 150 C threshold that was set. And what it's doing is, even like I said, even though you still have a little flow coming back, even though you still see some elevation of temperature at in the hallway there, which is the teal line, it's not able to actually come out of that room fully and expand in the rest of the house. If that fan wasn't going at the front door, you would see this line go up, and much like it does down here, all of the other rooms would go up at an approximate rate. When that went down and we made another opening, the rest of the rooms would go back up just as the same. So the fan is actually keeping the flow from going in there. And we saw this in the 2-story structure as well. So front door, I still have some positive flow. I should have said this earlier. Negative is flow into a space. Positive is flow out of the space. Still have some positive flow out of that front door, but when I'm looking at a fire on the 2nd floor in the bedroom, that fire can go to flashover, and I'm not raising temperatures in the rest of that structure above 93 C. So it's really not increasing temperature-wise the problem in the other structure, or the rest of the structure. It's also important to understand the difference between flow through a room and flow out of a room. So let's say you happen to make a poor choice. You go around the structure and you're trying to guess where the fire is. And and you think the fire's in the back bedroom, so you open the back window. Then you come to the front door and you open the front door to put the ventilator in, and you put the ventilator in and realize the fire is in the living room. It's important to understand what you're going to do to the rest of that structure. It was originally thought that because you're moving so much air, you are going to move all that heat and smoke through bedroom 2 and out, and it's not going to affect bedroom 3 or the master bedroom. It won't increase those temperatures. Well, when we look at the rest of the structure there, we are increasing temperatures in the orange line, which is bedroom 2, we'd expect, in the teal line, which is the hallway, which we'd expect, and in the living room. But then we're also increasing temperatures in the hallway, in the master bedroom, and in the dining room, and in the living room. And why is that? Well, because flow is all dependent on the temperature in the structure. So if the hot gases are at the top of the opening and there's cool air at the bottom of the opening, there's going to be a flow like this at every one of those openings. And it's going to pump heat into the rest of the structure. And you very, very quickly exceed that 150 C in the rest of the structure. So where you would have thought, even though I'm blowing everything this way and I've written off this part of the structure, I'm making it survivable for the occupants out here in the dining room and the kitchen, you are not. You are actually making it worse throughout the entire structure. Whereas when you have flow through the structure, or out the room, you do have a high temperature in that room, but you decrease and continue to decrease the temperatures throughout the rest of the structure. Now we take a look at I forgot I put this in here. Now we take a look at that one instance in the living room where I pull up and I have a firefighter responds, they show up on scene and they have fire coming out that front window. And their primary mode of ventilation prior to fire attack is starting the fan. So they do what they always have done. And they start the fan and they create a flow that goes in the door and out the window. I would have expected this to act much like the earlier one where I was flowing through the bedroom and out the back and it would increase temperatures throughout the rest of the structure. But what we actually see is, apologize, we're missing some temperatures on that graph apparently. Luckily all the Celsius ones are still there. So as we turn that fan on, which is this line here, we increase temperatures in the living room and we increase temperature in the hallway, which makes sense because our temperature sensor is really in the same room as it is in the living room. But in the rest of that structure, we don't actually increase it above 150 C. We keep it below 150 C. And that's where I'm talking about. It's actually burning outside the structure. Could we play the video in the bottom right? Okay. So if we look, this view here is looking down the hallway. So it's a camera in this wall looking down the hallway, and it can see into the back of the living room. As our fire grows, we end up with a ventilation limited fire. You can tell that by the amount of smoke that was coming out of the front decreases and our temperatures decrease. So if I look at this opening here, this is looking right down that hallway into this space right here. When I open that window, I expect I'm adding oxygen, I'm going to increase the size of the fire. So we go ahead and open that window and we allow some oxygen in, and as we're looking at that view, we increase and we start to see more temperature in there as we'd expect. We start that fan, and from the front view of that structure, I made it absolutely horrible in that living room, right? There should be no way it's survivable. I look down that hallway, and it's hard to read on here, but this is actually somewhere in the neighborhood of about 200 F, which is somewhere in the 120 C range or something like that. And 100 C, I'm sorry. And I'm not seeing that temperature. I should see hot gases in the back of that living room. And I don't, because it's pushing it all out that front door and all out that window. And because there's no opening on the back side, it can't actually increase temperatures in there. And you say, okay, well, you looked at temperatures. Should we look at gas concentrations as well? And I agree. We certainly should look at gas concentrations. So the equation I was talking about, a fractional effective dose, which takes into consideration CO, CO2, and O2, we look at that. And in normal engineering, so if I'm doing fire safety engineering, I cannot get above a fractional effective dose of 1. But what does that mean? That means you can't effectively rescue yourself from the structure, right? When this line is increasing, you're receiving dose. When it's decreasing, you're receiving less dose. When it's level, you're receiving a constant dose. As you can see, as these were increasing in the bedroom and the dining room, which are this bedroom here, which is open, and the dining room here, which is open to that living room, they're increasing. When I turn the fan on, it definitely changes how much dose of CO, CO2, and O2 you are receiving in there. Now, may it be a fatal dose? It's certainly an incapacitating dose. They are not going to walk out of that structure themselves. But it is affecting what's going on back there. And if I have a delay to putting water on that fire, I have done something that positively affects what they're doing. Is it something I would advertise doing? No, because we call it Mrs. Smith in the U.S., the old lady that you're going to her house, who you want to make sure you take care of like your grandmother. And if Mrs. Smith happened to be standing out front when you blew the air in her structure and all this fire started coming out her front window, she probably wouldn't be very happy with you. So, open concept floor plans create quite the challenge for these positive pressure ventilation fans. What we see is, because this is our two-story structure now, and we have a fire in that living room, that space is open completely to the rest of the structure. So any increase in temperature there is going to flow into all the adjacent rooms that are open. So there is nothing you can do with that ventilator other than increase the size of the fire and allow more heat to go into the rest of those rooms. It was thought that, much like the single story, if you pushed all the flames out the window, then you'd create the temperature outside the window instead of inside. But what happens is you have a two-story space here. So the flames continue to go up rather than across the ceiling and out the opening like we saw in the single story, and temperatures go up in the rest of the structure. Temperatures on the first floor and even temperatures on the second floor go up considerably. So those are at the 3-foot level, but you're exceeding that 150C. Now, in reality, you exceeded the 150C before you did anything, but you're still not giving them any additional benefit by applying the ventilator. So it was thought that, well, you just don't have enough openings. If you had more openings, you'd be able to have more flow, so you'd be able to push more of it out of the structure. So we take and made both of those windows open instead of one of those windows. And as we talked earlier in the presentation, we looked at fire burns in proportion to oxygen. So if you remove more smoke, that means you're adding more air. If you're adding more air, you're adding more oxygen. And rather than having temperatures get to somewhere like 150C, we're now seeing all the temperatures above 200C in there. And we get down to some of the other experiments where we just see that increase continue. So that's talking about the ideal situation. We have one window open and we have a front door open. And how does that affect what's going on in our structure? Now let's take a look when we have multiple windows open. So in the US, either the police officer broke all the windows or the well-knowing truck company that doesn't actually carry water walked around and broke all the windows for you, so it let all the smoke out. And you put you turn the ventilator on. Even though you're doing what you said you were doing before, where you're creating the flow, it's exhausting out the room, you'd expect that room to increase in pressure or temperature, and the rest of the structure to decrease in temperature, which is what we see here on the left. We compare that to what we do here when we create those additional openings, and it creates additional flow. That additional flow creates additional path of travel. And because we can't get all of the gases to flow into this room and out the window, some of them are flowing back out the top of that doorway, they start to flow into the other rooms. We actually are capable of lighting the master bedroom on fire by making an opening in the master bedroom, having a fire in bedroom 2, turning the fan on. Fan increases bedroom 2's fire size, which slightly comes back over here, lights the carpet on fire here, travels into the room, lights the TV stand on fire, lights the bed on fire, and we're able to ignite everything. So here's the video of that. We have done nothing yet. Nobody showed up. We have a fire in the back bedroom. This is a view of this doorway right here. So it's looking into the doorway. That's the bedroom 2 fire coming out. We make some openings. And as we make openings, we increase that fire size, and you see what happens there. So we open our front door, we allow more clean air in, and we turn our fan on at 8 minutes and 28 seconds. And it does something interesting to that flow. It does decrease that flow that's coming out of there, as I would expect it to, but it doesn't decrease it enough that the radiant energy from here isn't capable of lighting the carpet on fire. So as we watch, 2 minutes, roughly in about 30 seconds, we'll see that we went from flames on the carpet to flames on the dresser. And we have flames are just barely visible in the view back here. This is that window right here in the master bedroom. And as we continue to watch that grow, not only are we allowed to, or are we able to have flames coming out our bedroom 2 window, we can get flames coming out of our master bedroom window at the same time. So we can do a very good job of systematically burning the house down through the use of the positive pressure ventilator. So that was where we had the opening prior to turning the fan on. Is it different if I turn the fan on and then make the second opening? Let's say, for instance, I turn the fan on and I realize that there's a back door at the back of this house, and I happen to be around back, and I'm really interested in getting inside to make sure no one's in there. And I open that back door to get in there, and I crawl in, or I walk low in to try and search this portion of the structure, which is on the first floor. It's not on the second floor, so I should be able to get in there and do some searching without a problem. I'm not going to hurt anything, right? Well, when I start to do that, we ignite our fire. It's growing in this bedroom here. I am looking down the hallway at this doorway here, so the flow out of the top is the flow out of that doorway. And we see that our fire is flowing out of that doorway. Our fan's not turned on yet. Oh, I'm sorry, our fan was on, and then we open our door. So let's go back and look at that one more time. So we have flow coming out the top of our door. Our fan is on, and it's keeping most of the flow inside there. Ignore the temperature on there because that's only looking at the back wall temperature there. But so we have flow coming out the top, but it's not a whole lot of flow. Most of our flames are coming out that window. As soon as you'll see door open here is when that door got opened at the bottom of the structure. Much more velocity coming out of there, much more heat coming out of there. So if I happen to be the guy who's trying to get the hose up to the top of the stairs, and as you see how this house is configured, to get to the top of the stairs I have to make a complete turn to put water in that bedroom. So as much as I flow water up those stairs, it's never going to get into the bedroom and it's never going to affect the fire. I have to make the complete turn to make it happen. And I happen to be sitting there, or just getting there, as you happen to open the back door, things might feel like they're going to go really bad really quickly for me. If you happen to have a victim laying at the top of the stairs and the firefighters were crawling up to get the victim and you open the back door, you're redirecting that flow. It's making it less effective, and it starts to come out of the compartment. So we talked a little bit about, in the earlier presentation, about positive horizontal ventilation and vertical ventilation. And there is a very big debate in the US on which is best. So West Coast believes in vertical ventilation. East Coast believes in a combination of vertical ventilation and horizontal ventilation. Midwest thinks positive pressure is best. So depending on what US firefighter you ask, you could determine which one is the best. So what we want to do is understand how they interact. And in reality, they're tactical choices. They are not necessarily one is better than the other. So let's look at a living room fire here. And these are our temperatures in our living room. On the green lines are the temperatures when we did positive pressure ventilation. On the red line is when we did horizontal ventilation. And on the blue line is when we did vertical ventilation. Our intent is to decrease the temperatures in the living room to make sure that we're making it survivable for everybody else. So we allow the fire to grow. I'll talk in a second about why those are so different growths in the fire. But we allow the fire to grow, and we have the fire department come in and do something. And they all do the something at 6 minutes. So if we open the window and turn the fan on, our temperature decreases a little bit, but within about a minute, we increase the flashover, and we maintain that until we put water on it. If we just open the window and the front door, takes a little bit longer, because we're not accelerating the amount of oxygen going in there, to increase those temperatures, and it stays at that until we put water on it to decrease it. If we happen to open the front door, climb on the roof, cut a hole in the roof, and then see what happens, we notice that that takes a little bit longer. I gave them 2 minutes when we simulated it. I feel like it really takes a lot longer than 2 minutes if you have to climb up on the roof, but depending on the size of the structure. But we see very much the same thing happen. We hit a temperature that's an extremely high, unsurvivable temperature inside the room. So regardless of which one of those you're doing, if your only mission on the fire ground is ventilation, and you're going to do that to make things better for firefighters and occupants, it doesn't matter which one you pick. You're making it bad on all three, but it's in a very different mechanism. As a researcher, I want you to understand not that it's bad, don't do ventilation, because that is kind of the message, but that's one of your takeaways if you're not willing to think about it. What I want you to understand is why. So the horizontal grew slower than the positive pressure. Well, that's because it wasn't getting as much air because it was a natural flow versus a forced flow. Not only did it take longer for the vertical ventilation to occur, but when it does occur, we don't quite reach the same temperature. Why is that? Well, the hole we cut in a roof was 4 by 4. When we opened the window, it was 5 by 8. So we added more air with the window than we did with the vertical ventilation, and the temperature didn't quite go as high. So if you understand the concepts, now we can understand when we're working with these things on the fire ground. More interestingly is what happens after you put the water on. So if we think through it after we put the water on, or before we do that, we'll talk about two things. First of all is the change in temperature here. What you're seeing is 3 grants that occurred over an 8-year period in the US. The furniture that was purchased for the horizontal ventilation study, which is the red lines here, which is couches, sofas, beds. We purchased them from a hotel reseller. So we actually go in and buy the exact same couch 26 times. I get a lot of funny looks with the charges on my credit card, but we are capable of getting exact couches for the 26. We get exact chairs. They burn very similarly. We burn a bunch of them under a cone calorimeter to make sure that they're burning similarly, and we put them in the house and we burn them. Well, 3 years later, we go back to the same one, and we can't get the same couch. But, you know, if we get sort of the same couch, it'll be fine, right? It's only been 3 years. How much difference in manufacturing of couches can we have? So we get the same couches and we burn them and we find out, holy cow, they didn't quite burn as high. So the vertical ones are not burning quite as hot as the energy release and growth in the vertical one is not quite as much as the vertical or the horizontal one. And we talked to the guy who we got them from, and he says, well, the first time you bought them, they were actually manufactured in 2003. So they go through a whole bunch of hotels before I get them. They're fairly old. The second time we bought them, he had found an older hotel, and they were manufactured in 1999. So they were actually older than the ones that we had used for horizontal ventilation. The positive pressure ones we got, he happened to find a hotel that had water damage from a roof leak, and they needed to get rid of all their furniture. And the furniture was from 2007. So now my furniture is much newer. But what it's really important to look at is the evolution of how furniture burns in a period between 1999 and 2007. For the fire safety engineers in the room, when did they burn the couch to tell you how to use it in a smoke exhaust system? Does anybody know? About 1980, they did the tests at the National Institute of Science, which was NIST, or National Institute of Standards and Technology. They burned couches. They assumed, since they burned 50 couches in that experiment, that they'd never have to go back and burn couches again. We know how they burn, and you could use them in design fires for buildings. And those same curves are still used today for design fires. And they were before the blue lines were created. So it's evolved considerably. We have a lot of data on it. We're working on writing up a report that hopefully we can work to get into those codes. But it's a very interesting thing. We also want to look at what is going on throughout the rest of the structure when we're talking about this ventilation, because not only does it make things better or worse in the fire room, but we're really intending that the fire room is unsurvivable. No one can survive that anyways, based on the temperatures that they see when the fire is ignited. So in our particular experiment, we got to 1600 degrees F, or somewhere around 900 C in the fire room, floor to ceiling, before, what's that, at 4 minutes? So the fire department is certainly not there yet, 4 minutes from ignition. So that's a very unsurvivable temperature, and it doesn't really matter what you're doing to that room, but it does matter what you're doing to the rest of the structure. So we look back at that, and let's take a look at the dining room, which I don't have a picture of the structure, but it was off to the left of the living room. We see the same differences in growth of the dining room, with the exception for some reason we're able to increase the temperature pretty similarly between all three, and I think that's just how flow is created in between the door openings. But in horizontal, where we open the window and door, we're creating the most effective flow because we have the biggest opening. We increase the dining room temperature at the floor, which is the lowest line, above that 150C. It goes up to about probably 190C. In vertical ventilation, we're increasing it just to about 150C. Because we didn't increase the temperature in the living room as much, we don't increase the temperature in the dining room as much. And in positive pressure, we increase it just a little bit less than we do in the horizontal ventilation, because we're pushing most of that out of the structure, but we're also mixing the gases up in there much more because we're using a ventilator to do it. See the same thing in the kitchen. But more importantly, when we start to go down the hallway and we're in the bedrooms, it's a lot different. So we were able to exceed the 150C mark, which is this line right here. We exceeded that in this bedroom before we showed up, before we turned the fan on, but it dropped back down below that when we turned the fan on, or before we got there. When we turned the fan on, or when we made our intervention, in horizontal, we increased that temperature all the way up to like 130 at the floor, about 240 or 230 at the 5-foot mark. You're certainly not going to be conscious if you're in that room, but you might survive being in that room with horizontal. With vertical, it's much the same, but with the green lines, the positive pressure ventilation, the temperature didn't go back up as much as it did with the other experiments. And that's because you're further down the hallway, you're further away from the fire room, and that gas exchange is not as effective. What happens if you close the door? This is the even better part for those of you who sleep with your bedroom door open. This is a fire growth with the bedroom door closed. We did not exceed 71 degrees C in that bedroom in any one of those experiments with that door closed. When we did our intervention, we did absolutely nothing to the temperature in the room with the door closed. So if you sleep with your door open, you are well along the way to increasing the temperatures by the time your smoke alarm goes off. If you sleep with your door closed, what we've seen in almost all of our experiments is you could most likely be alive in that room, probably conscious, well into the fire department arriving. If you open your window after the fire's there and you leave your bedroom door closed and choose not to go out and you hang your head out the window, you could probably stay there until the fire burned out in the living room because it's that much different in the temperature inside that room. So being behind a closed door is very, very important. So this is good because, at least in the US, we teach young school children, if there's a fire in your house and you touch the doorknob and it's hot, don't leave, put a towel under the door and stay in your room. It's excellent. It's an excellent choice. But for some reason, when we get to adults, we don't quite get to that point because now adults sleep with their bedroom door open so that they can hear their kids at night, or they sleep with both their door and their kid's bedroom door open so that they can hear when something's going on at night. There's a very big difference in with it open and it closed. So most importantly, close that door or sleep with that door closed. So we took a look at...
Sorry, may I ask?
Yes, absolutely.
You're for me a movie star. So I try to ask the first question. But when you you choose a ventilation, horizontal, vertical, but when you integrate the graph of total energy,
area under the curve.
yes, I saw mostly on the vertical ventilation, the most energy goes away with the vertical ventilation. Is that correct?
Well, those are temperatures, so those aren't heat release rates, which although temperature equates to heat release rate, it is not a one-for-one equation to a heat release rate. As much as I'd like to reverse model all these to figure out what our heat release rate is, I don't quite have enough time. But in that instance, you would be correct that we released the least amount of energy. Most likely, because the temperature didn't go high enough, we released the least amount of energy throughout that. But our goal is not to release the least amount of energy, because that also means when you make an additional opening, let's say you break another window or you cut a bigger hole in the roof, the fire is going to grow again. And if you've given time for firefighters to get between where that fire is and where they get out of the building, and then you make another opening which allows it to grow again, you've put them in a pretty bad spot. in reality, if I were to do this, so I spent 15 years in the fire service in the U.S. as a volunteer firefighter. And today I look at ventilation very differently than when I was originally put into the fire service. Ventilation is phenomenal after water goes on the fire. Before water goes on the fire, all ventilation is not good for you. It's not good for anyone. But understanding what happens is important because you can't always control ventilation. My friend could open a window for me and think he's doing something good, and he really is not. So I have to educate him on why. I could hear glass break in there, whether it's because of the fire or someone broke it, and know that I need to move because I am now in a bad spot because something's going to increase. So the other thing we looked at with this project, positive pressure ventilation, was we looked at how does outlets and light switches impact the ability of the fan to push the fire into the wall space. So there was a concept that they thought that you cannot use this tactic whatsoever. It will never be effective because there's a light switch in that room, and as soon as you turn the fan on, it's going to push the fire into that light switch, which is going to push it into the wall space and into the attic. So we looked at testing that. We put 2 outlets, 2 light switches, and 2 lights inside the stud cavity of that wall, and then we put a piece of gypboard over the back of it to simulate that it was an interior wall of the structure. And then we drilled a couple of holes in the top of this one to simulate where a water pipe would be going through, or a water drain exhaust would go up through the structure to see, is there a difference between when there's no hole in the top of it and there's some hole in the top of it. So this is a video of, it's sped up, but this is a video of that experiment looking at those openings on the top of the structure. So I have, this is towards the front of the structure. This one over here is towards the back of the structure. But this is looking at that specific hole. And during the fire, we see that we are moving smoke through there. But as we look at the color of that smoke, it's quite light in color. If we were to guess at the temperature, it's relative to the color of the smoke coming out the window, it's much lighter, so it's probably much less temperature. It's actually probably just what can get through there. And if you looked at that in particular throughout the entire experiment, that's what we just watched in the video, I could surmise that there's probably nothing actually actively burning in there. It's probably just smoke that's getting pushed through the opening and out the top. And as I go back into the room and look, we've melted away our switches and our outlets. They're no longer there. As I look at the back, I see that that room was flashed over, and it melted the outlets, and it charred the wood a little bit, but most likely what we thought, there was no flames in there. It wasn't actively pushing the fire into that space. The one that we had openings on the top and the one that we didn't have openings on the top were pretty much the same. There was no really drastic difference between them. And as we look at the temperatures in there, we can see that we certainly didn't exceed anything that would indicate it igniting. And there's a very good difference in pressure, so there's some of the energy is being, or difference in temperature, so some of the energy is being lost. Well, let's compare that to when we take and cut away the entire top stud. It's not there. It's as if it was we call it balloon construction, when you construct the walls and then you construct the floors off of that. When we take that away and we have that completely opening, we have much different smoke color. We're seeing a much different production of smoke. You can see that there's active burning in the room. The room is right here. And as it continues to go on, the density of the smoke gets darker. It starts to come out more aggressively. And eventually, we start a little blowtorch coming out the top of the structure. So there's definitely flames inside that space now. Coincidentally, after we did this burn, I hadn't looked at the video beforehand. And it was lucky that we took the wall apart and put the fire out, because without looking at this video, I never knew that happened. I didn't notice that it came out the top. So let's take those 2 walls apart and take a look at it. And we see that the one that was completely closed, although we do have a good amount of soot buildup, there was some way to get air in there and soot went in there. It didn't really have flames, whereas compared to the one that did have flames coming out, we saw that we alligated all the studs in there. We were able to burn away some of the soot because the flame was such a temperature that it burns it away in there. So it was capable of moving the fire in there. Well, that makes sense, because the ability to move the fire we talked about before, the ability to move air, is all based on how much of an exhaust it has. In modern residential construction in the US, we don't have that entire top cord cut out. That's usually either drilled through with holes or it's actually fire stopped if it's a multifamily residential structure. So in most instances, there's really no way for that air to get up through there.
Is there normally also isolation for the sound or for the heat between the walls?
In multifamily, if it's between two units, so two apartments, there would be insulation in it. If it is not between, if it's just a wall for like a bathroom and a bedroom, it would be completely empty inside there. We don't have any insulation in that. I am not sure how the construction is here, but it's specifically in the U.S. If you take down a piece of drywall, there's definitely no insulation behind it unless it's the outside wall or it separates two units. If you live in a really fancy house, maybe they put sound insulation in the bathroom so no one can hear what's going on in there. I'm not sure. So it's all directly proportional to how much the space can exhaust. So now this adds another element to when do I use my fan or not. If I'm in a structure that was built probably prior to 1940 in the US, maybe a little longer than that, it was commonly built by building the two outside walls and then attaching the floors to the walls. So that wall itself ran from the basement of the house all the way up through the second story into the attic space. So in that type of a structure, I wouldn't want to use my fan because I do have a complete open chase where that can blow up through there and it's going to transfer the fire. But if it's a newer structure, and I know how they build the newer structures, they build the two walls of the first floor and then they build the first floor across it, and then they build the two walls of the second floor and they build the floor across that. It's got stops in there that's going to prevent that from going up through. So, last part here before we get to some questions. Hopefully I leave about 10 minutes for questions. There was two schools of thought or two theories when it came to using fans for positive pressure ventilation. So now the fire's out. There is no chance that I'm going to regrow the fire with the fan. We've completely controlled it. And we're going to look at what's the most effective way to remove smoke from that structure. There were two schools of thought. The first school of thought was you do it one room at a time. So you use the door to the room, and you turn your fan on, and you open the door, and you open that window, and you allow it to completely exhaust that room, and you close that door, and you move to the next one, and you do the next room, and you move to the next one, and do the next one. We called it systematic ventilation. So we took a look at that and said, let's test that. Let's see what that looks like inside a structure. So instead of burning the whole room, because then we would have a big problem, we burned one chair. We protected the chair with drywall so that it wouldn't light the rest of the room on fire, and it just created the same amount of smoke. And we let the chair almost completely burn out. And we had temperatures anywhere from, these are in degrees F, so anywhere from like 70 to 120 C inside that structure. And we said, well, when that temperature returns to about ambient, which in our lab is somewhere between 70 and 80 C, depending on how big the fire was that we built in there that day, we would say that that room has been ventilated and it's been cooled, and that's replaced the atmosphere in there. And as we do that, so we turn our fan on, which is this line here, and it decreases temperature throughout. But we notice as we open the bedroom, so the orange line is that bedroom, when I open bedroom 2, the temperature drops down and it exhausts it out. Then I close bedroom 2 and I go and I open bedroom 3 and it drops bedroom 3 down all the way. Then I close that and I open up the kitchen and it drops the kitchen all the way down. And because I never created an opening in the hallway, the temperature was still high in the hallway and it couldn't completely exhaust it out. So it was very similar when we looked at our CO2 and our CO concentrations in the structure. As soon as we made that opening, the line dropped down right to ambient, but when we had the door closed, it stayed up. So then we just said, well, let's just do this non-systematically. Let's open every window and every door at the same time and turn the fan on and see what happens. And what we saw happen was they all uniformly dropped down and completely dropped down to ambient. And so this one happened when we made that opening to when we're pretty close to ambient in the rooms I was trying to ventilate. We did not do, the dining room and the kitchen are going to be the exception because that's where the actual fire was, because we just took all the furniture out of the dining room and burned it in the dining room. So that, and we also didn't open those windows, so it didn't ventilate out, but it exhausts out and returns to ambient. That one took roughly 4 minutes. As we look back here, as I systematically did it, It took somewhere around 6 minutes. It took a little bit longer to systematically ventilate it than it did to naturally ventilate it. So that would tell me, as I'm comparing these two, that if I opened as many windows as I could, I'd be able to remove smoke as efficiently as possible. And when we think back to our cold flow data that I was talking about, we moved more air the more openings we made. If you're a mechanical engineer and you design a heating system that's a forced air heating system, and you want to heat that room up, you need a certain number of air changes to make sure you can heat it in a certain period of time. If you design an HVAC or an AC system to cool it down, it's the same concept. You need to change the air out in that room to actually cool that room down. Well, we're doing air changes. If the more flow we create, the more air changes we get, the better it's going to exhaust that structure. So this really upended it, because for me, this is what I had learned in my entire fire service career. Always systematically open the windows. That's the most effective way to get all the smoke out. Not only that, but you'll do it faster, because you won't have to pull all the smoke out at the same time. When in reality, you can open up to 3 to 4 windows in there, and 3 to 4 rooms, and it'll exhaust it all out very quickly. And we can take a look at that on the video. So as we look at these side by side, these are the 8 views of the house, and systematic versus non-systematic. So on the left, I'm systematically opening windows, and you can already see a drastic difference in the systematic ventilator, or the non-systematic where I've opened everything. You've got visibility back in all the rooms. I can see across all the rooms. Everything's lit up. Whereas in our systematic room, we are still slowly making some openings in here to get the rest of that to ventilate out. So where are we with this project? The hardest thing about research, and especially in the fire service, is firefighters want the answer yesterday. And they would like a yes or no answer. So do I use the fan or do I not use the fan? Is it good or is it bad? And the reality of that is we can't get there. Not that quickly anyways. These are 3-year projects. It takes quite a considerable amount of time to run the experiment. To run 25 experiments took us 2 months in our lab, burning every other day. So where are we? Well, we've completed all of the burns, and we're on this data analysis portion. So all 825 graphs, we probably saw, I think, like 30 of them that we've created. We're going through those, trying to compare them, trying to determine when something occurred, when it did not occur, if we can attribute it to the fan, or if it's not attributed to the fan at all, and it was just something to do with the fire growth. We're comparing those together. We're working on our final report and the final tactical considerations. What I've presented today has already gone through our technical panel, and they have said, yes, we agree with everything that you're saying. It makes sense for the fire service. Go ahead and present on that, and those are written up. There are still some that I'm writing, and the goal is to get that out by the end of this year. So that'll be in English on our website, hopefully no later than December 31st. We also develop online training programs for this, and we're working on that. We can't quite do the online training program until we've completed the report, so it'll be probably 2 or 3 months after that that we'll have an online training program, again in English, free to take on our website. So with that, is there any project-specific questions or even group-specific questions as to what I do, the research, or anything like that?
You have a very nice plant with buildings inside for testing. In my opinion, you are introducing a problem with your positive ventilation. Did you try a negative ventilation, so extracting the heat and the flames out of the room that's burning? Then you get...
So essentially to that, we can't make a fan that you could physically put there to do that wouldn't burn up the fan. Those gases coming out of that room are on the average of about, they're actually the adiabatic flame temperature, right about 1700 degrees F. So we would do significant damage to the fan, and the firefighter that had to put the fan there probably wouldn't be very happy with us afterwards. But the concept is absolutely true. The reason they went to this, they used to exhaust by sucking smoke out of the structures. They just couldn't get as much air change with sucking it out after the fire was out than they can with using the ventilators, is really the answer to it.
You can build engines for airplanes that work on the temperatures.
Oh, absolutely, but
Design it if you like.
if you wanted, but the fire service certainly probably won't carry them around. They've got quite a bit on their fire trucks. We're trying to convince them actually that what they do with the ventilator is increase the fire size in some rooms. Once I get to there, then we'll decide on the best way to get it out of the structure. Yes?
The presentation is all about positive pressure in the building while it's still burning. You mentioned
To try to determine the difference between the two?
Just to put in the ventilator in the building opening and blowing the air out of the building. Do you have any experience with that also?
So we didn't specifically test that for this project, but we have tested it. And it all goes back to the airflow. So when we're using positive pressure ventilation and you set the fan back from the opening, it entrains air in the air that's been blown in. It's kind of like if you trying to think of a good example for it. If you take a plastic bag and you put your lips up to the plastic bag and you blow into the plastic bag, you wouldn't be able to inflate the plastic bag fully because your lungs are of only a certain capacity with one breath. But if you hold that bag away from you and you blow just into the air, you're going to entrain air as you're blowing, and it's going to fill that plastic bag up full. So it's going to put more air in that bag than just purely blowing into it. The exhausting is very much the same. You only can suck out what can go through that fan, but the positive pressure ventilators can entrain more air and go into the structure. So whereas the negative ventilator is moving somewhere in between maybe 6,000 to 8,000 CFM, when we opened all of the windows on the structure and turned the fan on, we were moving somewhere between 18 to 20,000 CFM. So we're almost 4 times as much air was being moved when we were doing it in that method. So, but again, it's all based on the conditions at the structure, how well it works. I think we need both types of ventilations because sometimes you can't set a ventilator up. I mean, it may not work. It certainly does not work quite as well and as efficiently if you're 15 stories in the air and you're trying to blow air in the first floor and have it come out the 15th story. That's not going to be as effective, and carrying a fan up there, setting it in the window, and exhausting it out may be the most effective way to ventilate. So we need to understand both. Again, it's all about understanding how it works in my theory. If we understand how, firefighters are the smartest people I have ever met, even though they say they're not very scientific. They can solve any problem in the world that you throw at them, and they do it in seconds. And they're usually pretty ingenious solutions that they come up with. I mean, even at the fire station, in the U.S., they're having funding problems in one city, and their bells in their firehouse don't go off. But their printer prints out a printer page. And the firefighters found out that if they take a Coke can filled with coins, we have aluminum Coke cans in the U.S., and they set it on the edge of the printer, when the page come out, it's going to knock this Coke can off into the bucket. It's going to make a large noise, and they'll know that they have a fire call now. So the problem-solving abilities of firefighters just astound me for these guys that say that we're not that smart. And I'm like, you're geniuses. I wouldn't have thought of that. I have 6 years of engineering degree, and I would have not thought to fill a Coke can with coins and let the printer knock it off there. So I'd have probably tried to program a bell using a computer, and I would still be trying to figure it out while yours worked. So Detroit was the city that happened to. But understanding, if we give you the knowledge to understand what's going on, you can make the most effective choice. So in these single-family structures, that was the option. But it may be very well easier to exhaust it, pulling it out in other instances.
When you compare the situation in Europe and America, you use, I saw, constructions of wood. Do you have any experience with stone houses?
So,
and can you say something about it, if it have some results?
So we certainly did not test that, and the intent of this was to test content fires. So only the room is on fire, not the house. So to do that, we put up, in the U.S. we use drywall. It's gypsum board. It's a concrete board, has about the density of air. So we put that up on the inside of our walls. Very different than the stone in the walls in the structure. Here the stone will absorb much more energy. It's going to make fire growth considerably different. But eventually you'll hit the same point where you run out of air. And at that point, the reaction to that is probably going to be very similar, with the exception of our structure has the ability to dissipate the air or the energy, whereas the stone structures and the brick structures are going to hold that energy. And then that's going to, so in our structures, if I leave the structure closed for, I think we did it for 9 minutes, the fire doesn't start again when I make an opening. It just puts itself right out. Whereas if we had stored energy in the walls, it would be able to keep the temperatures up inside there so that when we made an opening, instead of decreasing temperatures, it maybe allow it to speed right back up again. But that is something we're very interested in because in the US we train in concrete training buildings, but we fight fires in houses that look like that. So we really want to know the difference in the two. We have a grant to do that, and that's coming up here shortly, so I will get the opportunity to do that. We also are always looking for opportunities to collaborate. We have had invites, we just have not been able to come up with the funding to travel internationally to do some of this type of testing, because we also do it outside our lab. We'll do it in the field. We bring all the equipment with us, we throw in all the sensors, we work with the local fire brigade to do the suppression for us, and we test it if they have an interesting building that we could potentially use. We're always looking for that, but again, the funding is the challenge. These grants cost somewhere between $1 and $1.5 million US to do. Most of it is in building the structures and doing that and the instrumentation. Our time is actually covered by UL. We have a really interesting relationship, whereas if I go out to get a grant to do work, UL is willing to cover my salary, and we can use all of the grant to get as much as we possibly can done. Whereas if they had to cover my salary with a grant, we wouldn't quite be able to do as much. So it's phenomenal that they donate this. The company is just amazing that they do this for us. Yep. Oh, I'm sorry. I'm around afterwards.
No, because we only have a quarter of an hour for the next lady, so we have to stop.
Okay.
It's only a quarter of an hour.
You have the 15-minute break now.